actually circuits that implement transfer functions. So first, just to make sure everybody sees this, and it's probably pretty obvious to us. If we have a signal Sx of S, and I'm going to do everything in the S domain, I'm not going to bother with time domain right now, and I have it coming in to two or more systems, this just indicates the feed is going this way. This will be the first transfer function, H1 of S. This is the second, H2 of S. And we could extend this indefinitely. You follow me? They're all in parallel. And I come out and I have a summing circuit here. I'm so sorry. I've been dealing with people all morning long. We've got a whole bunch of meetings, problems we have to sort through. And I'm not available right now, unfortunately. So when we have this, the output of this, that just indicates summer. All right, you add whatever goes into the two inputs. Do you follow me on this, class? Mm-hmm. And there can be any number of inputs to that summer. So I could extend this to have 3, 4, 5 in parallel. But the output right here is just an addition. So Y of S would be simply X of S times the quantity H of S, and call this H1 of S, plus H2 of S. Now that should make sense to you, right? Here's what happens though. Engineers have this knee-jerk reaction, parallel. That means multiply them together and divide by the sum. Do you follow me on this one? Think of resistors. They do a knee-jerk, they don't actually look what's going on. Follow me? Now the next is a series approach. And I think I've done this before here, right? One time, but I want to make sure everybody's got this. The next is a series approach where I have some X of S, and I can have H1 of S and H2 of S. And there can be as many as you want strung together. Where the output Y of S is really, if you take a look at the output right here, you have to show the direction of the signal flow. The output here would be H1 of S times X of S. That would be the input to that one. So the output here would just be H1 of S times H2 of S times X of S. Or the overall system transfer function, Y of S over X of S, is just H1 of S times H2 of S. Now here, the overall system transfer function is H1 of S plus H2 of S. Do you all see this? And you can extend this naturally as far as you want. You can also do combinations. You could have two parallel in one series, but I think you all see how to do this, correct? Here's the one people have trouble with. Just remember what I told you. Knee-jerk reaction in parallel, multiply this by this, divide by sum. That's wrong. Got it on that? Don't do the knee-jerk. Same with this one. This one they don't usually miss. They see it pretty clear. This one gets messed up. So I'm trying to warn you about the pitfalls. Now this is called a feedback circuit. How many have had feedback in some class? What class was it?
Not in class.
Oh.
Sorry.
Well, you didn't get in class? I don't know if they present this in laboratory work or not. That's the reason I'm asking the question. Because if they have, I can pick a different approach. Now, since they haven't, here's what I'm going to tell you. This is called feedback. This is a feedback loop or circuit, and sometimes they use the word negative. It doesn't have to be negative, but here's what happens. You're going to have an X of S. I'm going to do it all in the S domain. I don't want to mess around with time. That's the reason we have Laplace transforms, to get out of the time to make our life easier, from differential to algebraic equations. It comes into a summer right here. That's a summer, all right? Now it's going to come into something, and I know everybody likes H1 and H2. Here I'm going to use an A of S. It means a function that's going to amplify, usually. This is a standard thing. A of S. It's a transfer function. Could be S squared, could be 5S plus 2 over S minus 1, it could be anything. But it's a transfer function. Usually it's an amplifier. Then it takes a portion of this, and it goes through something called the feedback circuit. And this will be a beta of S, and then it goes back here. Now the output here, Y of S, is interesting. I'm going to show you, we're going to derive it, but I want you to see how I'm doing this. So in the future, if you're running the circuits like this, you're able to derive these things, because they don't have to be this simple. They can be more complicated. But and I'm going to give you some of them too. I want you to just follow me on this. Now, what I always look for is the input to the amplification section, the section after the sum. Follow me on that? You want to get what goes in right here. Well, what actually goes in at this point is going to be x of s, right? Plus what? Or actually minus in this case. Doesn't have to be a minus, could be a plus. Minus b of s times y of s, right? You all see what I've done there? Y is here. A portion, I didn't show you the path. This is being fed back to the input here, but there's a negative sign, it means it's subtracted. Does everybody see this? I want you to take a good look and make sure you do. It's critical. Everybody see that? That right here is beta of s times y of s. That's subtracted from the input, and so that's the value of the signal right here, right? Y'all agree? You're suspicious, I can tell. You're looking at me very skeptically. How many see it right here? Now you take all this right there, and you multiply it by the amplification factor, A of s, and that equals y of s. Does everybody see that? That feeds into the amplifier, the A of s, it's multiplied by, right? The output is y of s, isn't it? Now we get our overall system transfer function. I want you to watch this. I'm gonna ditch the s's. So I have x, right, minus beta times y, all times A is equal to y, right? Just broke it out so you could see it. Do you agree, class? Now what I'm going to do is this. Multiply that through, so I have x times A minus beta A times y equal y. Just, going through the math. Then I'm going to take this to the other side. So now I have y here, and it's times 1 plus beta A, and that's equal to x times A. You all see what I'm doing? Just rearranging. What I'm after is y over x. That's y of s over x of s is h of s, right? So the overall system transfer function here, h of s, is equal to y over x. I'm putting the s back in, and that means it's going to be a of s over 1 plus beta of s, a of s. This is very, very important. This is a feedback circuit. In this case, it's a negative feedback circuit, and it's the first time you've been exposed to it. Well, some of you have, in other classes or in other careers or something. But the thing about this is, usually speaking, you have an amplifier that's got a whole lot of gain. The problem is, it's got a very small frequency band it can work over. And you would like it to work over a much larger, because it'll go unstable. So what you do is add negative feedback, and it'll extend the frequency range, but it will lower the overall amplification. Now, I'll show you this in a second, right? And you can just kind of do the math on this. Suppose A is 10, and beta is, say, 1/2. Well, 10 over 1 plus 5, right, 1/2 times 10, is 6. So 10 over 6 would be less than 6, and I'm just using a single number. Do you all see this? It reduces the overall amplification, but it'll extend the frequency out to which it works. That's the way I like to think about feedback. It also stabilizes an unstable circuit a lot of times. All right. Now that configuration is real important in the actual synthesis. And I'm not going to get to synthesis quite yet, but I want to make sure you see this stuff. Is everybody clear now? No? Yeah.
Why are you solving for h of s instead of y? Did I miss?
Well, h of s is the ratio of output to input called the transfer function. Almost all systems, what you'll see is a block diagram where they have this. That's ratio of output to input. That's the critical thing. Because you don't know what the input's going to be. But if you know that transfer function, you can always predict the output. All right? Now, about the homework. Now for your homework questions. And is there an eraser? Oh. All right. So which homework problem was plaguing you? I didn't look at grouping, I'm sorry. Lydia, do you want to start? No?
I guess problem 4.
What was problem 4?
I don't have it written down.
Problem 4 in the book or in the?
It was.
It was a block diagram.
You got it? I got it. Forgive me for not bringing, I don't think I have problem 4 over. Just show it to me now.
I don't know if I have it or not.
Anybody have it? Looks like you have a laptop, you can pop it on. You got it?
Yeah.
Bring it up here. I did this for a reason. You need to be introduced to this at least the lecture before I lecture about it, so you're thinking about these kind of things. All right, this is the feedback problem. And so it's got plus and negative, so I'm just gonna show you what it has. It has x of s here, coming in. You can take your computer in 1 second. It's coming in, there's the feedback loop, plus, there's minus here. And then it has, first block has, can you just read this to me? First block has s, right? It has s over 2, right?
S plus 2 over s squared plus 3s plus 2.
Go ahead. Where's
Next
it
block
go?
has 2 over s.
This is 2 over s?
Yes, sir.
That is an integrator, by the way. And then this is y of s?
Yes.
This is a good one. Here,
That's going to be 3 over s plus 2.
3 over s plus 2 into, go ahead,
That's going to be 4.
4, just 4? All
Just 4.
right. And they want to know the output, right? Now, remember, first thing you try to do is simplify things as much as you can without getting into anything. Now, I'm going to show you this. Take a good look at this. If you haven't done it, now's the time to think through it. Ask yourself, how would I deal with this problem? Think about simplification first thing. Don't think big picture, simplification. What can we do with this? Is that not s plus 1, right? Times s plus 2? Do you all see that? How many see that right there? S plus 1, s plus 2, right? So I'm going to replace that. Next, what do we do? Anybody? How many see you can get rid of the s plus 2s? Y'all with me? Now make sure you see this. If you don't, yell at me. Because I got to make sure you see what I'm doing. Now I've simplified that, right? Now the next thing I'm going to say, that feeds into that. Can't I multiply these two? You all agree with that? So I'm going to just get rid of that block altogether. And I'm going to say this is really going to be, wasn't it 2 over s over 1 over s plus 2? Is that right, class? S plus 1, I'm sorry, S plus 1, you're right. S plus 1, thank you. That mistake was not intentional. All right, down here, what am I going to do? 4 times 3 is 12, right? Get rid of one of those blocks. That's 12. Now, I'm going to identify things. This is your A. That is A. That is the amplification, so to speak. It's the forward amplification factor. If in your transistor, I don't know if Dr. New covers this or not. You know what forward gain is? All right, forward gain is the amount that the signal is amplified, typically voltage gain, AV, right? This is the forward gain, right there, A. This is beta. This is the feedback gain, if you will. And now, when I worked through that problem, I said the output was going to be A of S, or I should say H of S. This is going to be the overall gain, transfer function, right? A of S over 1 plus A of S times beta of S. Let's do the math on this. A of S for this one is 2 over S times 1 over S plus 1, right? That's the gain A of S. It's divided by it's divided by 1 plus A of S, which is 2 over S, times 1 over S plus 1, times B of S, which is 12 over S plus 2. You all agree with me there? Now that is the transfer function, but it's not in the form we need. We need it in terms of polynomials on the denominator and numerator. Right here we have fractions in the denominator, right? So first I'm going to try to simplify this if I might. So I'm going to go ahead and say first 12 times 2 is 24. Let's go that route. So that's going to be just 24 here. Now, and remember, Whatever I do on the bottom, I gotta do on the top, right? Now I see I've got a common denominator here, right? I've got I'm going to get a common denominator. S over S plus 1 times S plus 2. And now, because I got 1 there, I'm gonna have to say it's gonna be plus the quantity S times S plus 1 times S plus 2 here. Y'all follow me what I've done? I want you to take a good hard look at this, make sure how many understand this. Y'all follow me? I took the 1 and multiplied top and bottom of 1 times S plus 1 times S plus 2. That's why this term is here, but I didn't multiply them out for a reason. You agree, class? Now, I take this bottom part and I just throw it up here. Do you all see? Because if you got 1 over X, it's really X. Do you follow me on this? So this bottom part right here goes right there. And I take it and I multiply it by S times S plus 1 times S plus 2. Get rid of that. And now I have this, right? 24 plus all that. Correct, class? I'm going to slow down a little. You see it, everybody? It is managing this stuff, organizing it. And you got to do it right. You can get tripped up in this if you go too fast. Now I'm looking, remember this is a big fraction bar right here. Now I'm looking at what cancels. You all see the S plus 1 cancels. I'm going to be sure you all see it, right? So get rid of it. Now the S cancels. Everybody? Get rid of that. So I'm left with S plus 2 times 2 on top. On top. Correct, class? Now on the bottom, you have to go and multiply this out. I mean, there's no way around it. So what am I going to be left with? On the top I have 2 over S plus 2 over, now I'm going to have this is going to be 24 plus, first I have S times S is S cubed, right? S cubed plus, then I have 1 times S plus 2 times S is 3 times S is plus 3S squared, right? And then I have, what's left after that? Then I have 1 times 2 times S, so I have 2S. Do you agree with me, class? I have all that, and that, I think, yeah, that's right. Correct, class? If we've got that, I'm wondering about one thing. 2. Wait a second. That beta times S, the A is 2 over S plus 1. And then times 12 over S plus 2. Yeah, okay. That's right. Yeah? All right. That's it. So that is my transfer function H of S for the overall system. Do you agree, class? What did the problem ask for? Did it ask for an actual solution for H of T or not? No? All right, but you all see how I got this? Now, if they wanted H of T, you would need to do it. First, you would have to take a look at this and see how you could factor it. These are a little tricky, all right? Off the bat, I know I've got an S plus 2 here, but I don't have the same thing over here. But, boy, this is one of those, I'm not sure how that would factor easily. Well, the problem is it's not a square, it's a cube. That's the problem. If there was an S here, it'd be great, but there isn't. All right, so this one's a little trickier to do. I'm going to leave that alone, but that's H of S. Do y'all see how to do that one? Now that's an application of feedback to a problem. We'll do a lot of these problems where you actually get a transfer function, then get the impulse response, the H of T. And that's important, you can see it. Another question. Yeah.
I have like a, I guess it's more of a conceptual question.
That's all.
Like, how does the transfer function relate to my input statement? Like for here, is it like for?
You multiply the transfer function, h of s, by x of s, and you get y of s.
Okay, so.
That's the
for
only,
any-
when I say transfer function, what I'm talking about is y of s, output over input, is equal to the transfer function of the circuit. That's it.
Okay, that's the same thing as doing the convolution?
Well, yeah, if convolving in time is the same thing as multiplying an s. And that's the nice thing about Laplace transforms, you circumvent convolution, and thank God. Because convolution with crazy functions can drive you out of your mind. There can be 5 different parts to them, easy. And you've ran into that a few times, right? Where you have crazy things like that. Well, Laplace transforms get rid of that. And I used to hate convolution. I'm still not there, you know, where I really embrace it, but I know where you're probably coming from, because I've been there. All right, good with that one? Now, any other questions? Because I figured you have a few. Yeah.
Could you do number 3?
Oh, you're gonna give me the values of these. This is an RLC problem. By the way, these problems you're going to get. Hint, you are going to get these problems. Many of these problems with R's and L's and C's. And asking for either the output given an input or the impulse response. The solution was provided, wasn't it?
No.
Oh. I thought it was. My bad. Help me out here. This is the input, right? Plus or minus. I'm going to go right to the estimate. X of S then, right? Then do I have a resistor here or not?
Yes.
All right. What's the value?
1.
Oh, that's
R,
beautiful.
L, and C are all 1.
That's great. I love these kind of problems. So here, the impedance of that is just SL, or S times 1. If R, L, and C, thank you, and C equal 1, this is the kind of problem that I welcome. Then I look at this, the capacitor has an impedance of 1 over S, and then the resistance is just 1, which I love. So this is just 1, right? Now, when I do this, I want you to just listen before you do anything. I want the output right here. I'm sorry I didn't put that all the way. What I want is this. I want plus to minus V out of S, right? That's it, correct? Well, what does that boil down to? It boils down to taking the input X of S. What is X of S, by the way?
At first, it's not
It's
given.
not
and
given.
it's-
They want H of S then.
Yeah, in the first part, it's fine to transfer, in the second part, it gives you an X of S.
Let's get the transfer function. H of S is equal to V out of S over V source of S. Call it V source here instead of X. Now, and I highly recommend you take my advice on this one. Box these parallel things. They're all in parallel, and just call that Z, call it Z1 for lack of a better term. All right? Z1 therefore is equal to 1 over the first value, or 1 over S, plus 1 over the second value, or S plus 1. I hope you can see I just take the impedances and invert it. Strangely enough, it's the same thing. If I messed up, it would still be right. So I have that as my Z1 of S. It's 1 over the first plus 1 over the second plus 1 over the third impedance. And then I look at this transfer function and I see it's simply Z1 over Z1 plus R. You all see that, which R is 1 too, so I'm gonna put down 1. You agree with me? Because it's a series voltage divided, correct class? So it's output impedance divided by output plus series impedance, right? Times input voltage. Is everybody with me on this? Now, once I have that right here, do you know what I'm gonna do? I've given you this hint a couple times. Divide by Z1. You know why? Because doing that will put a 1 here and a 1 here, and Z1 will only appear here, and there's gonna be cancellation. Do you all see this? So divide by Z1. When you do that, I get 1 over 1 plus 1 over Z1. Now notice that boils down to 1 over 1 plus, and 1 over Z1 is just 1 over S plus S, right? Plus 1. Nothing tricky, right? Y'all see this, class? All right, what is that gonna be? Well, do y'all agree it's 2? Let me just do this. This is 2, well, let me do it. It's S plus 2 plus 1 over S. Do you agree with me? Make sure you do. Please, just make sure you see what I'm doing. Now, what is my next step instinctively?
No, it's
Multiply by
Multiply
S.
S.
Multiply by S, top and bottom, right? So I get an S up here, S squared here, S here, and I get 1 here. What is that factor as?
S is 1 squared.
S plus,
1 squared.
you all agree with that? How many do? All right, that's H of S. Let's get H of T next. That's the impulse response. I want to do it because I'm trying to show you how I think about these things. All right, now, when I have this, I look at something, anything multiplied by S usually means a time derivative, doesn't it, class? You can get away with a time derivative. You don't have to. But when I look at this, I could say, since that's a double pole, you could expand it as A over S plus 1 plus B over S plus 1 squared. That's legit. You can do that. Do you all follow me on this, class? If you want to do it that way, it's fine, correct? How many see what I've done there? You've got second order pole. You have to put the first term plus the second, the higher power. Now, remember how to do this? I told you a trick. When you do this, what value do you go after? B, right? Remember, that's the highest order pole. Correct, class? So if you go after B, what do you get? Well, I'm gonna go ahead and say, I cover this up and I evaluate the remainder of that when S is equal to -1, correct? Because the pole is at -1. How many understand this? If I'm going fast, it's because I'm trying to cover more material than you should do. So I just make that -1, or make that plus a -1. Now, how you get A is up to you. Remember, I told you could get a common denominator and expand it, and then the highest powers, you look at the coefficients, right? That's absolutely acceptable. The other thing is, what? The other thing would be that you would take a derivative of this function, right? And evaluate it at the pole. Do y'all remember that too? And either one is acceptable. Most students that I know don't do that. What they do is get the common denominator and they look at highest power. So if we did it that way, we'd have S over S plus 1 squared equal to, and this would be A times S plus 1 minus 1 over S plus 1 squared. What I've done here is multiply top and bottom of this by S plus 1. And then I've combined them. Now, I've got the -1 already, that's the reason I got it. To get the value of A, what do I do in that case? By the way, you'll notice you could get it a couple ways. A times 1 minus 1 right here has got to be 0 because this is plus 0, right? Or A times S has to be S, correct? Which means A is 1. Do you all see that, class? I want you to take a look because I know I talked fast. Take a good look and make sure you can see A is 1. How many see that? You see it? I mean, can you all see this or not? I'm just looking. You can? All right, I've got to make sure. I'm trying to do my job here. So A is 1. All right? Let's do it the easy way. If that's 1, what does this go to in the time domain? What would our H of T be? Class? If I have 1 over S plus 1, it goes to? All right, e to the minus t u of t. Now, the -1 comes down for sure, agreed? What does 1 over S plus 1 squared go to? How many remember it's t times e to the minus at, or in this case minus t? Sure. So that's going to be minus t times e to the minus t u of t. Now I have a question. When you look at this, what does the final, in the limit as t goes to infinity, what does it go to? What does this go to when t goes to infinity? 0, right? E to the minus infinity is 0. It's 1 over e to the infinity. Now this one you say, well, t is going up, but e to the minus t beats it. All right, it goes to 0. This one will die to 0 too. Follow me? So the final system, it'll go to a stable value of 0. It'll quench. All right. if it's a transient, if you have an impulse into it, and that's important. Now, what input did they give you for this one? This is a good problem.
Y,
Right.
V and of t equals e to the minus 2t.
All right, we can do that. So now we have the transfer function for the system right here, right? So I'm gonna go ahead and say, my h of s is this, right? Or really this. So I'm gonna say my y of s is equal to, and here the x of t for this function was e to the minus 2t, u of t. And I know that goes to simply 1 over s plus 2 in the transform of that. Do you agree with me, class? Everybody see that? Okay, I'm just making sure every transform pair I'm using is obvious. If it's not obvious, yell at me, because it should be. So if I have that, that is the x of s that will go here, and it's multiplied by h of s. So x of s is 1 over s plus 2 times h of s. Well, h of s is s over s plus 1 squared. Agree, class? How many poles, or how many terms am I going to have expanding that? 3, right? I'm going to have an s over 2. I have to get the a over s plus 2 plus b over s plus 1 plus c over s plus 1 squared. Now, show of hands here, how many feel you can solve for these coefficients? I want to know. All right? Does anybody struggle with this? This should not be any struggle at all. If you do, I want to make sure you understand it. So if we wanted to get a, the pole is at 2, minus 2, correct? So I cover the pole up, and I evaluate what's remaining at minus 2, right, class? So at minus 2 plus 1 is minus 1 squared is 1, right? 1 into minus 2 is minus 2. So this is minus 2. Does everybody see this, class? A is minus 2. Do we get B next? No, right? Because that's as part of a second order pole. It's higher. Now we get C. Follow me, class? Are you with me on this, guys? You're all quiet. I'm making sure. Do y'all see it back there now? Do you see it? If I'm going too fast, just let me know. I'll slow down. All right, do you understand how I get that? Minus 2? Back there, in the back of the room. Yeah? All right, do you understand how this is going to be the next one I get? Because this is the first order, that's a second order pole. All right, now how do I get this one? Anyone? I cover up what?
S plus 1 squared.
And I evaluate the remainder at the pole, which is what?
-1.
Minus 1. Do you agree with me? All right, what is that value going to be? Well, minus 1 plus 2 is 1, into minus 1 is minus 1. Do you agree with me, everyone? So that's minus 1. Now, how you get this one, I don't care. You can do the derivative method, if you so choose, or you can go ahead and just get a common denominator and equate terms, right? Agreed, class? If you did the derivative method, what does it say? You multiply everything by s plus 1 squared. I'll do the derivative method this time. If I multiply everything by s plus 1 squared, I have s over s plus 2. So I've just multiplied the h of s by s plus 1 squared, the higher order pole. And then I take a derivative of this with respect to s. And that will be my value at b when I evaluate it, where s goes to the pole value, which is minus 1. So a derivative of this with respect to s is 1 over s plus 2, and then it's going to be minus s over s plus 2 squared. The way I've got that, I'm using the quotient rule on this one. If I take the derivative of the first function, s, it's 1, times the second, which is 1 over s plus 2, plus the first function, which is s, times the derivative of 1 over s plus 2, which is minus s plus 2 squared. Got it, class? Now, I evaluate that at s equals minus 1, correct? Well, minus 1 plus 2 is 1, over 1 is 1, so that's just 1. And then when I have minus 1 plus 2, it's 1, squared is 1. And then if I have a minus 1, it's 1. Agreed? So it's 1 plus 1 or 2. We're not quite done. This is a little more lengthy problem than I wanted, but it shows you every facet of a problem like this. Now, let's go back to the time domain. I want to make sure everybody sees exactly how we get there. When I take this to the time domain, what happens first term? Always put the weight down. I call it the weight. -2 first. People forget that, right? Then after that, that is 1 over s plus a is e to the minus at. So this is going to be e to the minus 2t u of t. Don't forget the u of t. Plus 2 over, and what is the s plus 1 going to do, guys?
E to the
Right.
t, u.
E to the minus t times u of t. And the next pole is minus, and remember, if we have this, right, the 1 over s plus 1 goes to that. If I square that, I put a t in front of it, don't I, in the time domain. So this is just minus t times e to the minus t u of t. Do me a favor when you're doing these things, make the t's pretty obvious because they look like plus signs sometimes, and I don't know what you did. So make the t obvious if you have to put a curl tail on or something. Everybody got that? Now that's the entirety of how you do that problem. And it's a good problem. How many tried that problem? All right, did you have any problems with it, or did you get it? You got it? You got it? You kind of got it. I mean, you understood this part right here? By the way, how many of you do the derivative method when you calculate the value of b right here? One person? I do it. You know, how many do just equate powers on s? You do it that? That's what they must have taught you over in the math department, because that's what about 99% of everybody that I ever teach in this course does. Nothing wrong with it. Any other questions? Because now we're going to cover something. The moment you've been waiting for, how to synthesize something. All right? Basically, how do you build it out of components that are available to you? And transfer functions, by the way, are really, you'll see that these things, when S becomes J omega, they are the frequency domain filter characteristics. And these are wonderful things to know how to synthesize, because then you can build equalizers if you so choose, or you can do all sorts of things. Get rid of hump and a line, all that stuff. So, first, we've got to make sure you know one thing that you were just exposed to. If I have x of s here, comes in here, plus, this is minus, here's my forward gain A, here's my reverse gain beta. I'm just drawing the feedback loop. This is a summer. And this is y. And I know the transfer function h is y over x is really a over 1 plus a beta, where beta is the feedback. We just did this, correct, class? All right, now, if I want to actually synthesize something, there's 2 ways, and I'll tell you where it is in the book. It's probably more than 2. I'm talking about 2. I think I gave this to you as a reading assignment too, if I'm not mistaken. This starts on page 157, and there's 2 methods. This is the direct form 1, the direct form 1, and I'm going to show you the way it works. If you have he has here, I want to be consistent with the book. He says, suppose your h of s is this. Suppose it's equal to b naught s cubed plus b1 s squared plus b2 s. And we could keep going, but that's good enough for here. And downstairs you have s cubed plus a1 s squared plus a2 s plus a0. I want to tell you what we're going to do. We're going to divide everything, top and bottom term, by the highest power on s. Now I got to tell you one other thing too that the book doesn't bring out. you have to have the coefficient of the highest power on S here as 1. So if it isn't, suppose it was 2, you'd divide top and bottom by 2 and make it 1. Do you follow me on that? This has to be 1 for that to work. So put a 1 down there and maybe circle it, say like this is the thing it's got to start with. Now, next thing you divide top and bottom by the highest power on S, which is cube in this case, right? So now it breaks it out as this. And you're not gonna just cancel, but you're gonna have B naught over S, B naught, sorry, plus B1, and then it's gonna be over S, plus B2 over S squared. Downstairs, you're gonna have 1 plus, and then you're going to have A1 over S, plus A2 over S squared, plus A3 over, I should call it, I'm sorry, call this A3, call it A0, plus A3 over S cubed. All right? All right, well, only thing I've done there, I've structured it this way, and the reason I'm doing is because I can synthesize that. Here's how. You see this right here? That right there is your A of S that would go in here. You all see that? Now, that's the one that appears here. Agree? That means this right there is equal to AB. So AB is equal to A1 over S plus A2 over S squared plus A3 over S cubed. You follow me on this, class? Now, how are we going to synthesize it? In a block diagram form, we put the A here, right? And that A would be this term. Then we put the then we put the B here, and you would break that. Actually, we can do it this way. If you wanted to get B, you would divide this by A given there, if you follow me on this, all right? Now in the book, I've got to tell you a few things, other things that happen in here. I'm inundated with messages. Let me do it this way too. I'm sorry, I want to say something. If you try to do it this way, you can do it this way, but I'm going to show you a way that's probably even better. What you can do is this. You can say, I have a transfer function here. Just call this first part, and I'm going to do it. I'll break it out. This could be B naught plus B1 over S plus B2 over S squared. Just call that H1 of S. I'm going to show you the simplest way. Then that's going to feed into another transfer function. That other transfer function is going to be 1 over 1 plus A1 over S plus A2 over S squared plus A3 over S cubed. And this would be H2 of S. This is actually the method he was talking about. So your input, am I out of time? What?
I have a test.
All right. I want to make sure I'm looking at 5 minutes at least, right? That's the overall input X of S. This is the output Y of S. Your transfer function is H1 over H times H2, right? Now, this first part, the way we implement it is kind of cool. I want you to see this. And I'm going to have to erase some of the section to show you. When I get done with it. When I take a look at this, I'm going to do a block diagram first, and then we'll do it with components. I won't have time for components today. If you take a look at this, if I have my X of S coming in there, I just need one block that says it's B naught, right? And then go through, that would be the output from this to here. Then I need a 1 over S. So what I'm going to do is bring down something and have 1 over S here. All right, 1 over S. Doing this. Actually, back. Push it back on. I don't wanna go that route, I'm gonna go this route. Because these are added. Then I'm gonna come down here and have a block 1 over s, just a solid block 1 over s, it's a multiplier. Then I multiply it by a function b1. That comes up here, there's a summer. Follow me? And then I come down, have another 1 over s, feed that into b2. This is the direction of the signal flow, and it comes up to the summer again. So the output here would be b naught times x of s plus 1 over s b1 plus 1 over s, see there's a 1 over s times 1 over s is 1 over s squared times b2. And so I've realized this chunk right here. How many see this? All right, now I'll get into this, because this right here is done with an op amp, and so is this right here, done with an op amp. Very easy to do. It's simply capacitors between the output and the negative input, and a resistor at the input, between the input and the negative input to the op amp. And I'll show you that. This is the one I want to get to. Now this one is the feedback. And here's what I mean by that. Remember, you were just introduced to this. This is a summer. That's plus, that's minus, right? Doesn't look like a summer, but it is. This right here is beta. This is the forward gain alpha. That's beta. Oops, there's summer there. And this is what it looks like. This is y of s, this is x of s. Your transfer function h of s is equal to y of s over x of s, correct, class? And what was that? That's a over 1 plus ab. This is the way you should do it. This is the explicit method 1. The one I was doing before, it wouldn't work here. I mean, it would, but it'd be more difficult. Now, when you take a look at this right here, you know I have the 1 that I need. All right? This is A. You'll notice A is 1. All right? It means beta is this. So in the feedback loop, the beta here is just A1 over S plus A2 over S squared plus A3 over S cubed. Are you with me? Take a look. That's A over 1 plus A times beta. All right, let me finish my thought, I'll get to you. Well, what is A? A is 1, which makes it wonderful. That means this is beta. Y'all see it? Go ahead.
So this method works if you build that part first?
Well, these are going to be implemented with circuit components, yes. I mean, by the way, it doesn't matter if this goes first or last. This, you could have the first section, or the last section first and the first last, because they're two separate transfer functions. You follow me? Now, to build this, take a look at how it works. If I want to build this circuit right here, and I hope I have time for this, it's in your book on, he shows this on page 158, but let me show you how to do this. So, I'm gonna come out of here. Let me erase this, because I'm gonna run out of room. All right, now, what I'm gonna do is have something, and I wanna make sure he uses some, he does have a good, he's got a summer right here. So now I put another summer right here. This could be either plus or minus, doesn't matter. And if I take a look at this, well, I need beta right here. If you take a look, I have to take this signal right here, and I have to first divide by, this is actually the signal flow. I have to divide by a box 1 over S here, and then I take it and I have to multiply it by A1. And then that has to come back up, that's a negative, so this is a negative feedback loop. Then I break it with another 1 over S here, A2, right? And it's gotta be negative there. And then I take a 1 over S again, so I'm running out of room, a 1 over S here, break it with an A3, or multiply it by A3, and put it to a negative value there too, negatively sum them. Do you all see this, class? Now, you'll notice that what I'm doing is I'm taking the output signal and multiplying it by 1 over s and a, so the input in here is y of s divided by s times a1. But this is exactly that, right there. You follow me on this, class? I know a lot came at you today, and I'm over my allotted time. I'm going to start next lecture on Friday building the actual circuit components with capacitors, op amps, and resistors. And you'll see that all this stuff, you can realize it. Then I'm going to show you like a transfer function that will be very useful. For instance, if you measured speaker output power versus frequency, and it's falling off like this. Well, if we could take 1 over that, so that the transfer function, create a transfer function, so if you get this transfer function times that transfer function, you get flat 1. All right? Then you could take that, and this would be a pre-amplifying before it went to the speaker, and you would have perfect sound even from crappy speakers. That's what Bose did. I'll get to that. All right. See you Friday. There's a quiz. All right. It's on Laplace transforms. In this case,